Hey everyone, today we'll be talking about bubble sort and insertion sort. So in bubble sort, we traverse through the array repeatedly, comparing adjacent elements and swapping the ones that are in the wrong order until we reach a traversal where none of the elements need to be swapped. Okay, so the worst time complexity occurs when the array is reversed. So let us use this as an example. So in the first traversal of this array, 3 is swapped with 2. We're going to get 2, 3, 1. And subsequently, 3 will be compared with 1, which will result in a swap. 2, 1, 3. So notice that the leftmost element of the array, which is the largest element of the array, will get pushed all the way to the right. So we can generalize this with the statement: each traversal sorts one element. Therefore, we require n minus 1 traversals to sort n elements. The reason why it's n minus 1 traversals is because the smallest number would not have to be sorted. It will be already sorted by the n minus 1 traversal, and each traversal would compare n items. It would compare n minus 1 comparisons, which give us a generic time complexity of O of n squared. In an insertion sort, the algorithm builds the sorted portion of the array one element at a time. You can visualize it using the following example. So imagine you have this array. The algorithm would sort of place a partition from left to right and compare the elements from right to left. So in this example, it will compare 3, and since 3 in the right position, it will move on. Then it will move on. It will place the partition here and compare. So since 1 is the target element, it compares with 3. Since 3 is bigger, it's going to perform a swap. And since there's no other elements for 1 to be compared to, 1 is in the right position at this current juncture. Now, it will move the partition again. 2 will be compared with 3, and since 3 is bigger, it's going to make a swap. And 2 is going to be compared with 1, and since 2 is in the right position, the algorithm is done. And since the partition has reached the end of the array, the algorithm is done sorting the array. Now, let's look at the time complexity of this program. Similar to bubble sort, the worst case time complexity occurs when the array is reversed. So let's say you have this array where it consists of n items and it's in decreasing order. In the first partition, which no comparisons will be made. No comparisons. There'll be 0 comparisons or swaps. In the second, which will be placed here, there'll be 1 comparison made. The third, I think you can see the pattern here. There will be 2 comparisons made. If we continue the process after the end partition, so we have traversed through the arrays, there will be n minus 1 comparisons. We can simplify, so we can generalize this to an equation. The number of comparisons is given by 0 plus 1 plus forming a series. And we already learned in math class the generic equation of this of a series is given by NO2 times plus multiplied by the first term and the last term. In this case, the first term is 0, last term is n minus 1, which simplifies to order of n squared. Alright, let's look at implementing bubble sort and insertion sort. We'll begin with bubble sort. I will first show you how to implement a classical version of bubble sort before sharing with you an optimization hack. So, in bubble sort, let's define a bubble sort algorithm. We will repeat the process for I in range of the array. So we will. That basically means we'll be traversing the array n times, and in n times we're going to be checking for every index from range of 0 to length of the array minus 1. So we're checking index 0 all the way to n minus 2. We will compare the adjacent elements, and Python offers the array of index is more than the array after it, we need to cause a swap, and Python offers a neat trick to simplify the swapping process. So we can just index and voila, we have swapped the elements. And after traversing the array n times, the array is sorted, so we can just print out the array. And let's test this out. Oops. I should have n length of array. Oops. Yep. And voila, the array is sorted. But now, look, this line causes an issue. Not a direct issue, but an optimization issue. We're traversing through the array n times to make sure the array is sorted. But as we looked before, you only need this if the array is in reversed order. If the array is partially sorted, this is considered an overreach. You don't have to perform that many traversals. And now, if this concept doesn't make sense, let me show you the optimization hack, which not only makes the algorithm more efficient, it simplifies the whole process. So instead of this line, we're going to add in a Boolean flag, calling it sorted equals to false. And this we can call it the optimization flag. Now, while the array is not sorted, so this process will repeat until the array is sorted, we're going to firstly set sorted equals to true, and I'll explain why. Now, it's going to perform the check, right? It's going to perform the traversal, and if it finds that a swap is necessary in the traversal, that means the array is not sorted, not completely sorted. As a result, the sorted flag becomes false. Now it makes sense. If the traversal does not necessitate a swap, that would mean the array is completely sorted and the flag will remain true, ending this process.
Now let's run this code and we'll get the same answer. Now let's move on to insertion sort. Okay, let's begin by defining an insertion sort function. It's going to take an array. And remember how I emphasized that in insertion sort, the function, or rather the algorithm, would partition the array. So let's define that. So for let's define that process. So for partition in range of the len of the array. So this creates a partition from 0, 1, 2, 3, all the way to n. But let's make this more optimized. So we don't need to check for 0, because when you partition at 0, there's nothing for the element, nothing for the program to compare the element with. So it is overkill. So to simplify the process, we're just gonna start from index 1. So for each partition, we're going to take a look at the pointer index, which lays at the partition. And if you remember from the previous portion, the pointer index essentially describes the target element, right? It points towards the target element, which is what we want to sort within the partition. Now, let us define the partitioning process. So while the pointer index is more than 0, right? If it's equal to or less than 0, if it's equal to 0, that would mean that it's at the start of the index. There's nothing for you to compare to, so the process cuts that. And the array and the adjacent array before it is bigger than the target element. Then we're going to perform swap, and from the previous part we know that a swap can be performed using the following code: array at the pointer index plus 1 at the pointer index. And since the target element is shifted to the previous position, or rather one position down, the pointer index must also be decremented. That's a word. And once the process is done, we would know that the array is sorted. Let's test this out. And let's test this out. And voila. So we've taken a look at bubble sort and insertion sort and looked at the implementations. Now, if you have any questions, leave them down in the comment section below, and see you next time. Thank you for your attention. Bye bye.